So, how are things? How was the project? Was it what you expected it would be, the workflow, depending on what you've been covering so far? Was there any surprises in the terms of the traffic that you saw? What did you guys take the video of? Yeah.
Well, we were surprised when we did we did like a short one and a longer one. The short one, it was, I mean, what we expected. It took a shorter time to buffer for when we use the wired connection. But for the longer one, the wired connection only did a lot more than the wireless in the first couple seconds, and then it was pretty much the same rate for both after that. So it took almost the same amount of time to buffer.
Okay. What kind of video was that?
It was just a 330, like a regular YouTube video. It was regular quality, it wasn't high quality.
Okay. But did you notice that depending on the contents, things were different, depending on how much motion there is, kind of things. Right. So yeah, I'll read the report. For the next project, I would actually like for you to do something that interests you. I would suggest some options, but I think it'll be, given the fact that many of this technology, you might have tried something, I'll give you like a framework, but more of try something that you may find interesting, kind of thing. Given the fact that a lot of you seem interested in video games, that may be a good thing to investigate. Right? So I'll assign it the next lecture. If we have the midterm on Friday, right? So it'll be in class, open books, open notes, sort of how much we have covered so far. If there's any specific questions, let me know. Okay? So we're continuing on our journey. First, for a while we spent on trying to understand what multimedia is, and now we're trying to understand what are the issues, systems issues in using those, right? We started to look at the different kind of networks in the last few lectures, and also something on how these videos turn out in practice, I think. And the next issue is the how do you manage resources inside an operating system? This has been a perennial research topic, trying to understand how your machines, how your operating systems can deal with these media objects, right? One of the things you may have noticed when you run these, both the encoding and the viewing, right? They kill your machines in different aspects, right? When you're doing encoding, you probably notice that your machine is kind of, your CPU load went up really high. But the way they interfere with your work is a little different than the way the decoding would work, right? So when you're trying to do the encoding, you may notice that your processor CPU went really high. But you should be able to proceed and do other stuff. Whereas when you're decoding, you may not use as much CPU, but it may interfere with what you're trying to do a lot more, because there are some constraints on how this video is shown to you, especially when you're encoding. You don't have a deadline, you don't have time on when this thing should be finished, whereas when you're trying to decode it, you want to watch the video in a certain pace. And you may notice that if you're trying to watch a high definition video, most machines may not be capable of showing you giving you a smooth pace, right? And I think some of you mentioned that you did watch high definition video and still able to see it in a full, the way you would expect in a TV kind of stuff, but most of the time it doesn't happen. And so we'll get a little bit sense of what's really happening. And it all boils down in some sense to the operating system which manages the systems. And essentially, it boils down to resource management, right? And we looked at this. If you're taking that course in operating system or real-time systems, you would have gone much deeper into both these aspects. In general, the resource management problem is trying to figure out how to manage the resources in your machine. Resources can be anything. It could be a CPU, it could be a memory buffer, it could be a network card, network disks, and all those things. And the key here is how you manage them, how you allocate different things to different entities in order to get the benefit that you want. Right? And it can also be multiple CPUs in a multi-core system. And the reason, one of the reasons why the management is important is when the resources are plentiful, it doesn't matter how you assign it. But when the resources are bounded, you have to be smarter about giving the right resources to different components. And especially when you're talking about multimedia, as you probably noticed, they require lots of resources, so you have to be careful on how you do this stuff, right? So this is one graph I sort of like, and this sort of, so when you read papers, if you are doing research in multimedia and all those things, this sort of a graph sort of makes a lot more sense. It essentially shows on the x-axis some time, right? So it talks about 80s and 90s and 2000, all those things. But it's not really important what it is, but essentially this is the time. And the y-axis talks about some certain applications, right? What is important is technology sort of goes through these three different phases, right? This phase, right? Resources are insufficient to do what you want to do, and it's not very interesting to be in this phase, right? So if you're in 1980 and you wanted to watch high definition video in your laptop, you're out of luck. Your laptop could barely do, it's as far as a calculator, so it could barely do calculations. So you can't really do that much. So, I mean, there's no code, there's no interesting stuff here. And if you're in this phase, things are so powerful that it doesn't really matter what you do, right? So when things become really powerful, so one of the example they give us, if you're doing network file access, for the most part, if you want to investigate, I mean, most of us do file transfers on a routine basis. You probably notice it's sort of an issue when you're trying to download, say, a movie or something, a gigabyte or so. If you talk about downloading a terabyte, then you sit and pause because it takes a while for you to get it. But for the normal part, this is not something that you really worry about, that you take that for granted, and you probably don't even have a course in trying that, right? And the similar thing can be said about high quality audio. For the most part, we deal with MP3 files all the time. They tend to be fairly small, transferring them, all those things are fairly small. But when you get to a point, right, so the interesting stuff in research perspective happens out of here, right? If the resources are really constrained where you can barely do anything, it's not that interesting. And if it's really free, and then it's trivial. You want to be sort of here where if you're kind of smart, you get something, and if you're not smart, it becomes insufficient, right? So one of the examples of that is the amount of computing power, right? Most modern laptops have dual core, right? Or some of them even have 4 cores, right? What that means is you have enough CPU for certain tasks, right? So that means when you have more processing, you are kind of in the border on either case. So when the whole world moves sort of to here, then you won't worry about the resource management, right? So do you believe that your laptop processors are fast enough that you would have to worry about processor allocation as a problem for, say, multimedia encoding or decoding? Let's start with decoding, right? For decoding, do you think that on a multi-core processor, you would have to do something smart about it, or how would you decode your video and stuff? What are the different kinds of ways you can think of decoding a video? Let's go step back to the MPEG video, right? MPEG video with IPB frames. What are the sort of resources you need for decoding the MPEG video? Do you need memory? Yeah, sorry.
Oh, I was going to say you just need to be able to translate the macro block box.
Mm-hmm. So what kind of resources do you need for doing those? Yes, so we need to be able to generate these frames, right? Let's say this is our video with 3 frames, right? And let's say this happens to be I, this happens to be a B, this happens to be a B for whatever reason, right? What are the kind of resources you would need to play this video? Yeah.
We need memory to store the compressed frames, and you need the CPU to actually perform the calculations to decompress them, and then you need more memory to put the decompressed frames to be shown on the screen.
Yeah, you need lots of memory, right? You need lots of memory to store iframes and then the decoded frames and all those things, right? And you need processor to do this decoding process, right? And in general, because of the way that all the quantization tables and all those things are constructed, you tend to operate in integers, not floating points. So the modern processors ought to be able to proceed okay. And you also have extra instructions just to help you with these things. So the CPU, the computational part, your modern processors are optimized for, and they have SSE2, SSE3 instructions. So essentially, this helps you with this stuff, right? And then you have the memory, right? You have to keep frames in a certain number of frames, depending on how your thing is processing, depending on how many things you need for this prediction. You may have to keep a few frames in memory, and you have to sort of spit them out into the display at a certain rate, right? So you need lots of memory. Do you think we have enough that we should worry about it? What sort of a thing do you think is a reasonable memory for a laptop?
2 or 3 gigs.
Yeah, 2 gigs seems to be like what you, unless you're buying really cheap machine, 2 gigs seems to be a decent size, right? And let's say two core is sort of the reasonable stuff, right? For this sort of a machine, have you reached a point where you won't have to worry about the decoding performance, decoding resource management? What would be the simple naive algorithm you would use to run a decoder? Let's say, how do you allocate your CPU? A naive allocation. Naive does not mean it's bad, right? I mean, in this case, naive could be okay, right? Naive I mean like very simple, right? How about if you give 1 core to the decoding process? Right, you allocate 1 core, no more resource allocation. The resource allocation is 1 core goes to your decoding, and 1 gig goes to your other memory, right? Would that work? So in your laptop and you want to decode a movie, you basically allocate 1 CPU to the, so 1 CPU and 1 gig goes to this decoding, right? And the other thing is you have to keep, when you want to decode, you have to keep doing this every 1/30th of a second, right? So you have to keep sending the frames out, right? So you just allocate 1 to the decoding process, and you have the other CPU for your other tasks. If I did that, would that be okay? Would that be something that would bother you? Thinking of your own laptops, would that be a burdensome stuff? Who wants to take his time? Who agrees with this notion that giving one pre-allocating 1 is okay? Okay, who? Yeah. So 3 of you, right? So the others, do you guys disagree? Who disagrees? So, what do you think? Would that be a good idea to do that?
I'm not really sure.
Can you think of reason why that would not be a good idea? Yeah.
Well, putting a lock on a processor core and on a certain chunk of physical memory wasn't going to go very well with the OS. Or
we changed the OS to make that happen, right? We changed the OS so
well,
that
then most users might not like that because that's using the assumption that every user is only doing one thing at a time when they're using the most important thing that they're doing at the time is the multimedia thing, which might not be the correct assumption.
So, is that always true? Can you make an assumption? So when can you assume that users all they're doing is video, right?
I don't think you could ever do that because, like for example, it might be someone that's watching a movie while they use Photoshop. In which case, if you log a core for that, then they're not going to be very happy about Photoshop running like poorly.
So I think in that example, you're bringing up two things, right? One is users may be more flexible in what they're trying to do, and you also brought up an application Photoshop, which could potentially use both the core, right?
Mm-hmm.
So if you're doing Photoshop can take as much CPU as you can throw at it, so it will probably be better to have this sort of stuff, right? But if you think about it, right, there are some cases where this is okay. So if you're watching a movie in a full screen, there's nothing else running, right? This may be a good thing to go, right? What it also points to is you may disagree with it when I say it's 2-core, right? So when I change this to 4-core, right, you tend to get less resistance, right? And the latest is what, 7 cores, right? The Intel does 7 core, right? So when you have 7 core, right, then you don't much care. I mean, unless you are, so the percentage of users who is going to care becomes smaller and smaller. I'm sure there's one human being who wants to use all the 7 cores to do stuff, and they would be upset. But for the most part, when you have more cores, things go away, right? And that's important, right? That's important because whatever we read from the book and everything, they'll talk about something as being important, the resource allocation is important and all those things. Never underestimate the power of naive approaches which just work because the hardware moves us to here, right? And you may not see it in the literature, but that's always there in the background, right? When the hardware gets to a point where all these things become not an issue, then you don't particularly care, right? We'll talk about real-time scheduling and all those things, but remember, the future is towards going down this path when resources are plentiful in all the sense. So as long as the resources are plentiful, you're kind of not really worried about it, right? So for example, if I have a course on how to encode audio, right? How to encode your MP4 audio or something. At this point, it'll be sort of boring because just do whatever you want. Machines are fast enough, kind of thing, right? So, but we're going to talk about real-time systems and all those things. But remember, most machines don't do many of this real-time stuff. Most machines don't really implement all the stuff that we'll talk about. And you're kind of okay because the hardware is fast enough, right? And that's a part of the distinction. So again, going back to the operating system course, right? So we had a notion of processors. And processors are basically a program running, and we allocated a notion of a PCB, which is essentially a data structure, which keeps track of all the resources allocated to a particular process. And the main thing you are trying to worry about there is, once you have these processors, you want allocated resources, and you want to allocate resources based on some goal, right? When the amount of resources that were needed was less than what is in the system, right? So in this system, if all I wanted was one CPU and 256 meg of memory, right? Life is too boring, right? Because you want one CPU, I have two. You want 256, I have 2 gig. So essentially, it becomes no big deal. But when the amount of resources that you want is more than what is there, then the question of fairness comes in. The question of who should get fairly how much resources comes in. And so you spend a lot of time trying to figure out whether you should give to IO bound or CPU bound or what have you. But essentially the idea there is to figure out what is the best way to allocate the scarce resources among competing applications in a certain sense. And what we did talk about in the traditional operating system course is the notion of real-time systems where these things have some sort of a deadline. And again, if you took a course in real-time systems, this is probably all you spend your whole course talking about, right? So the notion of real-time systems is depending on what kind of application you want. These applications have some sort of a time constraints. So you can't schedule them whenever you can. They require certain tasks to be done at certain times. And if you couldn't do it at a certain time, then there is some penalty to be paid for it, right? So they expect processes to be happening at a certain time. And the penalty may be in the case of real hard real-time systems such as a nuclear power plant or something. Maybe that the plant falls down and takes everything along with it. Or it may be the case of a video where if you don't show certain frames at the right time, then your video, you may not like the way the video looks. There's not as much of a damage as you would for a hard real-time systems. But there's still some sort of fun. You like to keep these videos going at a certain rate, right? Especially if you watch these YouTube while you're doing encoding, you'll notice the video would be pretty choppy, and depending on how much the video means to you, that may or may not be acceptable to you. But these things have a certain time constraint, right? And the notion of that is this notion of a deadline, which says that when you should have a certain thing done, right? And the deadlines can be hard or soft, and again, that goes back to how important it is to miss the deadline, right? And we'll go through some of the more classical view of what real-time systems need to put things in perspective for what modern multimedia systems do. And again, the modern multimedia systems are driven by this sort of a world where over-provisioning, this is essentially what you're trying to do is over-provisioning. You have so much resources that a naive approach works as good as an optimal approach because you have a lot more renewable resources, right? So again, in the case of if you take a real-time course, you worry about real deadlines in real-time courses, whereas here you don't worry about that much, right? So the real deadline is, if you're talking about control system, or you're talking about your car auto ABS brakes, right? So those systems, if you don't brake at a certain time, you have catastrophic failures. Whereas in the multimedia system, if you don't put a frame at the 30th second, it's bothersome, but it's not destructive. And in terms of the bandwidth requirements, the other stuff is the traditional real-time systems worry about responding to an event. The response itself may not be that resource intensive. So it may require that when you press the button, it'll shut down the system or something, right? The amount of data that is transferred is not the key. The time is the critical component. Whereas here we're transferring large amounts of data, right? So the amount of work you have to do in a given server tends to be a lot larger, right? And we'll see what that is in a little bit, right? So in the case of so if you think of this, the multimedia, a real-time system, maybe you have certain periodic tasks to happen. So you have a notion that every frame has to be put up every 30 seconds or so. And you want the processing to be finished. So you want to get these frames at a certain pace, decompress them, and then put them up on the screen at the required frame rate, right? So when you see the traditional way of looking at these description, people talk about every 30th of a second, you have to do some processing to put up the frame, right? So the idea is every, let's say, this is 1/30th of a second. You sort of expect to do some sort of processing, generate the frame, and then send it off to the display stuff, and then you have this, you have something like that going on, right? How do you expect, let's say for a CPU, how big do you expect this stuff to be? Knowing what we know about IP and B frames. And clearly, if this happens to be more than this, then we are out of luck, right? So if it takes you, half a second to compute, to do the processing, then we are out of luck because the process is not fast enough. And you expect it to be smaller, right? The relationship to these things, do you expect them to be the same, or do you expect them to be predictable, or how much time do you expect to process these things? Think of iframe and B frame. Do you expect the iframe to take the same amount of time to process as a B frame and a P frame, right? And different frames, right? Do you expect them to take the same amount of time? You said no, right? What do you expect? Which one do you think?
Well, in the iframe, there's more the iframes are bigger, so there's more data slowed in. But also you don't have to do the motion vector stuff with the iframe because it's all there.
And a PFB frame, you would.
There's less data flowed in, but there's a lot more.
Is there less data actually?
Well, P frame is smaller, it takes up less space than an iframe.
Yeah. But the amount of data that you need for processing a P frame, right?
Well,
You have to have the corresponding. Sorry.
I guess loading in a P frame is a small amount of data, but you send the same amount of pixels to the screen.
Yeah, you send the same amount of pixels. I mean, hopefully the decompressed image will be the same size, right? But the amount of data on the P frame itself is small, but the P frame operates on an iframe, right? Or iframe or a previous P frame, I mean, previous sum frame, right? So if when you're operating on the P frame, you have to have your old iframes, or for MPEG 4, you can have up to 32 different frames, right? So you have to have all these frames. So your motion prediction, all those things are applied to those previous frames, right? So depending on how complex the scene is, your translations may be complex or not, right? Right? So what I mean is, like, if let's say you have the full MPEG-4 object-based system. So if your iframe had an object here, and P-frame basically said move this object from here to here, right? Move it from here to here, like move it by a small amount. Then the amount of processing you have may not be much, right? So you're doing some calculation. You have to have this old buffer. You have to have all the iframes, and using that you predict to move where you want to move. If it's a large object, right, you would have to do a little bit more compression. I mean, computations to move the object, right? When you have 32 of such frames, you may have to do the calculation. The calculation may not take more time depending on particular thing, right? What this means is the amount of time that you take here, it's rarely predictable, right? It keeps changing depending on what you're watching, right? It keeps changing depending on what the particular thing is, right? You may notice it if you're running your Windows-based machine, and if you run the taskbar, I mean the task operation to see how much CPU you're using. As you're watching this movie, you'll see that the amount of CPU, even at the fine grain, keeps changing, right? So what that means is what we're going to see for the next week. So when you're talking about real-time systems, I mean, you're talking about scheduling, right? One of the things you should remember from the scheduling from the operating system perspective was you always can do a better job if you knew the future, right? This is what we did throughout the operating system course. If you knew the future, you can do a better job. Use the past to predict what the future is, right? All the LR and all those things are basically trying to predict from the past what the future is, right? In this case, if I knew what the future is, if I tell you that you're going to take this is, let's say, X, and this is sort of X, right? If I tell you what the X is, then it becomes a lot easier. If I don't know what this is, right, then that's more realistic, and that makes our life a lot harder, right? It makes our life a lot harder because if this X tends to be this much, and let's say there is another task Y, right? If they happen to be like this, then I'm able to do what I'm supposed to do. But if it turns out that this X becomes bigger in a particular slot, then I may not have the CPU to be able to schedule them, and that becomes a lot more trickier than what you would do if you knew the future, right? So one of the things that you want to do with these real-time systems is I can build a hard real-time system if I know the future exactly, if I know how much resources you would want, if I know everything about the system, and they are predictable and bounded precisely, then I can say, then I can build a system essentially by saying that if you have, let's say, if you tell me that you're going to need X amount of CPU resources every so often, right? I can allocate this much and give them to you, right? And if you add another task which needs, let's say, Y amount all the time, I can say I can service that too. And if you want another task which takes this amount of processing, then I can tell you, no, I cannot deal with that because I know precisely that you want X, you want Y. you also want the z, but z would mean that I cannot allocate something more to you because I'm already allocated and I'm full, right? But if you make this sort of squishy, then it becomes a lot of, it is a little bit weird, right? If I look at the worst case behavior, then I can still say, no, I can't. But if you say the amount of time to decode a frame can be anywhere from 0 to x, if I allocated x to make sure that you can decode that frame, right? That means there may be times when you only took this much of CPU, so I won't be able to service you, right? So it depends on what I wanted. If I want to do the worst case behavior or the average case behavior. In real systems, you want to do average case behavior. Your laptops are all operating in average case behavior. So if you're watching a DVD movie on your laptops, you get, it works okay for the most part, except times when something's happened and you may notice that your movie freezes. That's okay because you are in the average case you set to work, right? Yeah, in a more theoretical, in a more rigid sense, in real-time systems, you want to perform admission control, where when you go into the system, you tell the system, this is what I want, this is how much time I'm going to need, and then somebody decides that whether that can be serviced, right? Depending on your specifications, and if they think that it can be serviced, you are let in, right? And somebody decides what the schedule should be. Somebody decides how these things should be organized, such that the system can give all of them the right stuff. It performs a reservation, which means that if you have another task, if you have another process coming into the system that cannot preempt any of this stuff. So if this is what the system was, X and Y will get that slot regardless of anything else. And any application such as like a Word or PowerPoint or something would get the remaining slot, right? So that's the notion. And once you build the schedule, that's supposed to give you the guarantees, performance guarantee that you wanted when you enter the system, right? And the main goal is to find the schedule which will give you the guarantee that you want. And you also want to make sure that the other processes don't completely stop, right? So if you only had the two real-time systems running and then nothing else is able to get in, then the system will be unresponsive, and depending on what you're trying to do, it may or may not be what you like. So in your laptop case, if I gave one CPU to your video decoding and one to PowerPoint, then that means that nothing else will get anything moving, which may or may not be acceptable to you, right? And also you want to make sure that the others don't start, and you also want to make sure that the real-time tasks do not suffer priority inversion, right? Priority inversion is another topic that you hear from operating system. The idea here is a low priority task should not be holding a higher priority task, right? And it may happen in the case of, depending on what you're trying to do, you may notice some of that effect in some sense. Right? If somebody is reading your disk, if somebody is doing something on your disk, you may notice your DVD program will stop because somebody is trying to read the disk, and then that's slowing, even though you were allocated a CPU, unless you send it all the way to the system, right? You will notice that your disk will freeze your DVD program, even though it get all the CPU. And you want to avoid that sort of a behavior. You want to make sure that the real-time nature spreads across the system, so that when your process is running, it gets all the resources it needs to proceed, right? So, in a more canonical sense, when people describe a real-time task, you describe each task by 4 constraints, right? The 4 constraints are the task starting point, the processing time, task deadline, and task period, right? So in the case of if you have a start, if you think of this as a time, S is a starting point when a new period starts, right? You give it how much it needs to compute, right? How much processing it needs. You say this is the deadline, and then you say period. The idea here is you want something to be calculated every period time, starting at start, and within each interval you need E amount of work which needs to be completed by the task deadline, right? So if you're talking about a video system, you may say that the starting time is 0, right? And every 1/30th of a second, your next frame will come, right? And I will give you a task which is like which takes amount like X or in the example E, and it has to be finished by a certain amount of time so it can be sent to the display, right? And that's how you describe your different algorithms, the different tasks or processes coming into the system. There are two main classic algorithms that we need to get a sense of. But before we do that, we want to make sure that there's no congestion. We want to make sure that the schedules are non-overlapping, right? So if the next request happens to be before when you finish, then you have a conflict and you cannot allocate that. And you can also talk about whether these tasks are preemptive or non-preemptive, which is same as what we have from operating system. Preemptive means that this particular task can be stopped and then restarted later. Non-preemptive means that this cannot be stopped, right? So our goal is to find a feasible scheduling, right? So again, in the case of a non-preemptive, so if you have like two different tasks, if you have non-preemptive model, this lower priority in this case would hold the resources and would not let you proceed, and it'll become more clearer as we proceed. But essentially, the idea here is there are two tasks that you know have to proceed at a certain rate. You have the high rate and the low rate. The high rate was scheduled, and then there's nothing else, so you schedule the low rate. But since it was taking a long time, since it couldn't be picked out, right? The high rate would miss its schedule because the low rate would hold on to the CPU, right? So the thing is, you have to first figure, in the classical model, you have to first figure out if you can schedule this new task, and if you cannot, you have to be able to pick the stuff. So you have to do simple calculations to figure out whether a new task can still proceed to can still be scheduled, right? So if you're expecting, in this case, if you want another new task which requires a new space of Z, then you cannot because the amount of time is more than what you have, right? So the first model is if you take an example, this is a very popular algorithm, right? It's a static algorithm. It's optimal. It's static because you do it statically. There's no dynamically changing the periods and all those things, right? So the algorithm is simple. Essentially, when you have a task which is periodic, right, you schedule based on the frequency in which the requests come, right? The request with the higher frequency is considered to be higher priority. The request with the lower frequency is considered to be lower priority, right? And it's considered to be optimal because for a static algorithm, meaning like new processes don't come in and leave the system, this is optimal because you cannot, if the rate monotonic says that something cannot be scheduled, then there exists no other algorithm which can schedule that particular task, right? Again, these are more theoretical because when you come in, these tasks have to tell you exactly how much time they're going to need. And again, that may or may not be trivial because in a real system, you're going to have these different frames which take different amount of time because they require different amounts of forward and backward lookups, different amounts of buffers, all those things. So we can't really give these times. But if you could do this stuff, if you could have a period, then this is the algorithm to use. So here's the illustration of how this algorithm would work, right? So you have two tasks, the light gray and the dark gray. And given that you give higher priority to the ones which happen frequently, the first one gets the higher priority, then the lower one. So essentially that means you're allocating them based on their priority. So you first you finish the, if you have a preemptive system, right? You first do the light ones, right? And since they both come in at the same time, you have to finish the light one which is higher priority, right? And then you allocate, you finish this one. But while at this point, the gray one comes back again because it's a higher frequency, right? but since it's a high priority, you have to finish it before you finish the remainder from this section, right? So this is the schedule you would have if you're operating on a preemptive system. Does that make sense? So you have two tasks, right? One with a certain request, the other with a certain request. The first one is high priority because it happens often, right? The second one doesn't happen that often. So if you schedule them in a preemptive fashion, the first you have to, that's the process one is high priority, so that gets scheduled, and then you do process 2, right? But halfway through, the process 1 comes again, say it finishes, and then you finish this little one, right? It's a viable stuff because presumably the deadline is over here for the black one, right? So you finish, so this is not the deadline. So the black one finishes before the deadline. So both the black one and the process 1 and process 2 finish before the deadline. The process 1 deadline would have been here, right? It finishes before that part. Process 2 deadline would be over here, and they finish within the deadline, right? And in the case of non-preemptive, this is sort of what will happen. So essentially, you start the high priority one, right? And this one started, but you couldn't interrupt it because it's still in process while the next one comes in. The next one came in somewhere here. So it would have to wait a little bit, and at which point the next task came in, so it gets scheduled again. So you have a different schedule, but they all still meet their deadline. So it's allowed into the system, right? So either of these schedules would still solve the request that the tasks have, right? And these are optimal algorithms as long as you knew what are the different tasks and what they were doing, then this is a good way to go, right? And again, we know that from our discussion on EPIC and all those things, we may not know what the precise stuff is, but this is good to know what is the best to do, because traditionally people can compare the algorithms with the performance of this one, right? If you cannot possibly do better than this one. So if your algorithm that you're developing, a dynamic algorithm, cannot perform better than this one, so that gives you a bound of how good you are compared to an algorithm which knew the future perfectly. Does it make sense? And again, if you take course on real-time systems, you'll spend a lot more time on this kind of stuff. The optimal dynamic algorithm, which make decisions based on dynamically, is the earliest deadline first, right? Where you have a bunch of tasks and you figure out what tasks to schedule based on the deadline, right? The ones whose deadline is coming earliest gets to go next, right? And its complexity is n squared. So here's the example of how this may proceed, right? So for the process I, the deadline would be here, right? So this particular, the 1 has to be finished by deadline here, di1. The 2 should be finished by di2 and so on, because it's repeating that phase. And for the process 1, the amount of work is 1, and the deadline is here. Amount of work is 2, deadline is here, and so on, right? So when you start, right, which one would you schedule? So the deadline for this one is here, deadline for that one is here, right? So which one would you schedule first? For the earliest deadline? Which is the earliest deadline? The 1 or 2?
J.
Yeah, J, right? So you schedule that first, right? And then you schedule, so after this point, right, the deadline for this one would be here. The deadline for that is over there. So that's the next one. So you run this one. After this point, the deadline is here. The deadline is, whereas the deadline is over there. So you get this deadline, right? And if you schedule this way, then essentially these tasks will still be able to make their deadline. And any other task which your traditional operating system, the time scheduling task would get scheduled here, right? If you're running, if you have a non-real-time system, if you have a non-real-time like web browser or PowerPoint or so, they would get scheduled at these intervals, right? And again, all these things depend on how accurately you will be able to predict this stuff. If you over predict, what will happen if you over predict? If you predict more than you require, right? What happens if you predict this one to be more than what you require? You waste your stuff, right? You waste your time. So depending on what the operating system can do, right? Either it may be able to release whatever you didn't use to somebody else, right? Or it may just give it to you, right? So if you ask more than what you want, you may end up wasting stuff. You may end up rejecting some stuff because you said you wanted half the stuff and you only use 1/10. So you end up not letting somebody else, right? If you underspecify, what will happen if you underspecify?
And you'll miss deadlines.
Yeah, you'll miss deadlines and you won't have time to finish your whatever you have to finish, right? So you want to get it right? Because if you said you want to take 1 millisecond to do the decoding, the OS will give you 1 millisecond, right? And then you find out that you actually needed 2 milliseconds. Then the other millisecond, you basically on your own because you didn't schedule this real-time stuff. So the other one is like fighting for the other things. So you may or may not be able to finish your task. So you want to get it right? So all this is on the premise that you are able to predict how much you need, right? And so you can compare these two in terms of to see which one gives better performance for your particular application. So there's example here. We can sort of work through this on the next class to see what kind of schedule these two will produce. We are sort of out of time, and we'll continue with that. So before the exam, I'd like to finish this topic of scheduling and stuff, and see you on Wednesday.